Good afternoon, this is Hanuman, Professor in ECE Department. Today I am going to teach an elective course in the 5th semester, which is System Design through Verilog, which is an advanced subject in digital electronics mode. Now today we are going to see what are the different topics related to Verilog, and this is an advanced course in digital circuit design, and what are the prerequisites we need for analysis of this Verilog subject, which are basic concepts in digital circuit design like gates, combinational circuits, sequential circuits, and how to design them with the help of basic logic gates, and understanding the conv maps and more digital concepts. And next we need to have what are the keywords, what are different kind of constructs like if else, while statement, case statement, that is nothing but switch statement in C language. We need to have minimum programming skills to understand Verilog. And then what are the course outline of the subject, introducing the Verilog HDL. Everyone knows what is HDL. HDL is nothing but hardware description language. And we know that we have two kind of languages in hardware description language. One is VHDL and second one is Verilog. And for the industry perspective and project related or research related, it is always helpful to learn Verilog well, because Verilog is mostly industrial supported language and it is very close to C programming, because the constructs which we are using in HDL is mostly close to C language. And then learn various digital circuit models. What are different kind of digital circuit modeling techniques? There are three kind of modeling techniques. One is gate level, second one is behavioral level, third one is data flow level. We will explain this one in later classes. We will understand it properly in the next further classes. Now next one is writing test benches. This is another very important thing. Students need to check their designs with the help of test benches in the software. And this is also another important topic every student has to learn when they are completing this course. And next, at the end of the course, every student has to complete their mini project. That is nothing but case study. We are giving different kind of designs. For example, UART or SRAM controller or traffic light controller or dice game. So all these we can design with the help of digital coding skills, digital logic skills. And once you get the hardware part, we can design that with the help of any one of the modeling techniques. And then we check this whether our design is correct or not with the help of test benches. Once we get the results, that is called, in programming, that is called simulation. So once the test benches are actually verifying all the user test cases for the design, then we get the simulation results. Once they are okay, that indicates that our proposed design is correct. And next, this is the course plan for Verilog. First one is introduction to Verilog. Next, there are three kind of modeling techniques. And first, what is introduction to Verilog? What were the things we need to cover? So all the programming related basics we covered here. For example, what are the keywords used? Keywords. What are the operators? Different kind of operators. And there are some programming related basics we need. That means how to represent characters or numbers. Those kind of things we need to learn in first unit, Verilog. Introduction to Verilog. And then there are three kind of modeling techniques: gate level, behavioral level, structural level. And then synthesis of digital circuits using Verilog. And finally, different kind of Verilog models, which is case study. Actually, unit number 6 is not there, but we are proposing it as a case study. But this is completely, the syllabus is only 5 units. And then 6th unit is Verilog models it is nothing but case study. It is like mini project, which is helpful to get the students familiar with what they learn in this course. Then these are the textbooks, which are helpful for student to learn. Once the class is over, they can understand or more data they can collect it from. The first one is Advanced Digital Design with Verilog HDL, where the complete syllabus is framed. And if you want to refer more, you can also go with Fundamentals of Logic Design with Verilog. And then a Verilog primer by Bhaskar, which is covers a lot of examples. If you want to really see the number of different designs using if else statement, you can go with primer, because each kind of syntax we have multiple examples available in this book. So these are the books. And now we will start the introduction part. In the introduction part, this is the first computer having very, very small. It's just computing arithmetic. But see the size of this computer. It is very, very huge, and it have almost 25,000 parts, and it is Babbage's difference engine. And then in 1854, we have first level Boolean algebra referred by George Boole. That's why we always call this is Boolean algebra. Boolean algebra. Why that name comes? That scientist name is Boole, who proposes different kind of logical operations. But what is inside this logical operation? That is very, very fundamental. Daily we learn arithmetic. We are doing in childhood also, we are doing only three things: addition and multiplication, or we can call it as into. Exactly, logical operations also needed them. One is if it is a plus, it is called OR gate. If it is into, it is called AND gate. And then there is a usual operation. We see nature always gives plus minus, electron proton, negative charge positive charge, electron hole. So in the same way, we always need to have one gate called inverter, familiarly called NOT gate. NOT operation is tilde. That is called tilde. So if you represent some statement, if you want to write it in Verilog, for example, if this is the output y is equal to tilde a. What it performs? It performs the inverting operation. That means if you want this operation in Verilog code, you need to represent it like this: y is equal to tilde a. Before that, there is a keyword. I already told keywords are very, very important to write a Verilog code. Assign y is equal to tilde a. Here tilde is NOT operation, y is output, a is input, assign is the keyword. And if you write like equation format, such coding style is called Dataflow style. Okay, clear? Now he proposes three basic logic gates. They are AND, OR and inverter gates. So these three are collectively called AOI logic. Actually this is inverter, so it is collectively called AOI logic. Next, there is always first they proposed in 1854 Boolean logic. Then there is a connection between them that is proposed by the scientist. So Lee de Forest in 1906, entirely new electronics he proposed, which is called digital electronics, where he combines logic gates with vacuum tubes, because those days transistors are not available. So he draws some logic behind. So how AND gate is proposed, how AND gate operation is performed with the help of vacuum tubes. Then how OR gate is performed with the help of vacuum tubes. That is proposed by de Forest. And then this is evolution. So initially we have vacuum tubes up to 1946 or 1950s. Vacuum tubes rules the world. Even radios, telegraph machines, any kind of electronics related, analog related machines are completely built with vacuum tubes. We already know that vacuum tubes are bigger in size, less in lifetime. So the size is very, very bigger, and mostly they are replaced continuously. They need to replace their electronic components. So vacuum tubes era is over by 1950s. They introduced transistor in Bell Labs. So transistors those days are BJTs, bijunctional transistor. We know that. What is the transistor symbol? There are two kind of transistors. One is NPN and another one is PNP. So these two transistors, so initially they built transistors. Automatically transistors are very, very minimal in size, so that the electronic circuits gets reduced in size, and the lifetime is also improved in transistor, and leakages also very less. So huge advantages. In 1980s, they proposed, because one of the disadvantages of having BJT in circuits is, the major important thing is heat and noise margin. These two are very, very important disadvantages in BJT, and number of transistors incorporated in a chip is less. That's why they go for another technology, which is CMOS technology. So CMOS technology, even though they are introduced very earlier in BJT era, but the fabrication of CMOS is very, very difficult. In those days, in 90s, 60s and 70s technology, not supporting CMOS fabrication, because the equipment is not supported. So later in 1980s, enough research is established to fabricate NMOS and CMOS, NMOS and PMOS, because CMOS is comprises of two logics again. One is PMOS, second one is NMOS. So once CMOS design comes to market, so the number of transistors incorporated in a single chip getting increased, and noise margins getting better and better, lot of huge advantages in CMOS, getting a new world called VLSI comes. So VLSI introduced in the years 80s to 90s, huge research done in those areas. Now we have almost 3 nanometer design. See, initially CMOS starts with 220 to 180 nanometer in 2000s. Later it is reduced to 90 nanometer. Later it reduced to 45 nanometer. In 2015 it reduces to 22 nanometer. In 2020s it is reduces to 7 nanometer. All phone manufacturing, Samsung, iPhone, what any goods now having chips of 7 nanometer. Now that research comes to 3 nanometer. So once we get 3 nanometer, we don't go beyond 3 nanometer. That's why nowadays we have so much of hearing about quantum technology. So silicon or germanium can't go less than 3 nanometer. We have some physical kind of constraints are there. That's why we go for quantum technology. That is completely a different kind of electronics or technology. So this is evolution of digital electronics. It starts from 1910 up to 1950s. Vacuum tubes rules the era. Then 1950s to 80s, BJTs ruled the electronics. Then comes CMOS. And now in 2020s, CMOS also getting a final edge because it is almost coming to 3 nanometer technology. And also the operating voltages almost reaches 2.5 volts, which is very, very less because the breakdown of silicon is 0.7 volts. And now it is operating at 2.5. It is just an edge of 1.8 volts. So that is very, very less voltage. We cannot drive more gates, output gates with this kind of power. So that's why scientists think about different technology nowadays. And later, another important point is CMOS is later replaced by FinFET technology. Now all the cell phones are manufactured in FinFET technology. So this is about evolution of digital electronics through ages. This slide is particularly different kind of images related to technology. This is vacuum tubes, and there are capacitors and transistors. This is one CMOS technology comes in 1980s. See, there are a lot of ICs. This is also, see, the huge space, older technology in BJTs. And then this particular thing is very, very important if you really want to understand what really a digital signal. A digital signal is comprised of only 2 digits, 2 symbols. One is 0 and second one is 1. We cannot simply tell it is 0 volts. In reality, in real time, the voltage is continuously changing. So what is reality behind what is logic 0 and logic 1? And then we are going to understand what is noise margin at low level, what is noise margin at high level. So to understand them, we need an entire 15 minutes class, because first we need to understand what is VOL, what is VIL, what is VIH, and what is VOH. And then what is noise margin at low level? It is the difference between these two. What is noise margin at high level? The difference between these two. And first, what is 0 and what is logic 1? So in CMOS, 0 to 1.5. For example, if the battery is charged up to, that means 0 to 5 volts. Usual thinking, 5 volts means logic 1, 0 volts means logic 0, binary 0. That is not correct, because analog signal is a continuously fluctuating signal. So the voltage is ranging from 0 to 5 volts. So we marking 2 intermediate points. One is at lower level, it is 1.5. At higher level, it is 3.5. So between 0 to 1.5 volts, which is treated as logic 0. Between 3.5 to 5 volts, it is treated as logic 1. That means we cannot fix it at 0 volts, because in reality, capacitor is continuously charging and discharging. So once the capacitor is charging the voltage up to 3.5, we treat it as 1. Once the capacitor discharges up to 1.5 volts, it is logic 0. Okay, these two are very, very important. We cannot directly giving more knowledge in this simple class. It needs entirely 50 minutes to understand what is that. And we have one more important thing. What is strongest 0? There are 2 words which are very, very important. What is strongest 1? The strongest 0 is 0 volts. What is strongest 1? 5 volts. Okay, that means the strongest 1 means the entire, it reaches the maximum voltage 5 volts. But it is very, very important. Even 3.5 volts is also considered as 1, but it is called weakest 1. Weakest 1. And what is weakest 0? The weakest 0 is 1.5 volts. Okay. And what is noise margin? The noise margin means VOL minus VIL. And here VOH minus VIH. These are noise margins. Okay. And here logic voltage levels. Because it is a course introduction, I am clearly telling what are the important things we need to understand. Okay, so this description will clearly tells what is VOH level. What is O here? This is very, very fundamental to understand. What is O? Output. So output voltage at high level. What is VOL? Output voltage at low level. And this is output side. See, V not representing output voltage. VI indicates input voltage. And similarly, what are the input levels? VIL, VOL. So input low level and input high level. So with these four, we can draw these noise margins. We can find noise margins. Okay. And then a simple inverter. What is CMOS? It already told CMOS is comprises of one PMOS inverter and one NMOS inverter. And when PMOS and NMOS connected to a common input signal, which is here called as V input voltage, and the output voltage by the nature itself, if you connect to PMOS and NMOS and you give common voltage to both gates of this MOS, the output is always complementing of the input. It is natural phenomena. We can't do anything. It is just a natural phenomena. That is a basic understanding. See, even NAND gate and NOR gate also comprises of this logic only. For NAND and NOR, we have a parallel combination at the top, series combination at the bottom, and NOR logic, they are just reversed. Series at top, parallel at bottom, like that. So here, to understand what is inverter. Inverter means if you give input 0, suppose if the input is 0. And first we need to understand for PMOS, if input is 0 volts, it is on. For NMOS, if input is 1 volt, 1 volt means it is 5 volts. That is logic 1. It is on. And it is vice versa. That means if input is 5 volts, PMOS is off. If input is 0, NMOS is off. If input is 0, PMOS is on. What is on? It is a short circuit path. It provides a short circuit path. 0, NMOS is off. So it is open circuited. It is open circuited means Vout is directly connected to VDD. What is VDD? VDD is always set at 5 volts. So there is a directly low resistance path from VDD to output. So what is output after a certain amount of time? It is nothing but VDD. See, it is not directly getting 5 volts instantly. There is a capacitor. This capacitor is getting charging and it reaches lastly after a certain period of time, it reaches 5 volts. What is the time? The time is called rise time, TR. Again, it is a different kind of a class. It needs again another 50 minutes to understand what is rise time, what is fall time and all. And then see here, the input voltage is 0. Now we are getting input output 5 volts. That is inverting operation. Suppose if the input is 5 volts, then what happened? PMOS is off, open circuited, NMOS is on, closed circuited. Now the ground is connected to output. VDD is disconnected now, it is open circuited. Now already previous operation, the capacitor is charged at 5 volts. Now this capacitor starts discharging to ground. So this 5 volts getting discharging and after a certain amount of time, once it is less than 1.5 volts, it is called 0 and it's discharging in fall time, it is called fall time. So finally it reaches perfect 0 volts, strongest 0. So this is called inverter. Now I am giving 5 volts, finally what I am getting? 0 volts. So this is inverter operation. Similarly, we have NAND gate, NOR gate. Because why NAND gate and NOR gate are universal logic gates? So much fundamental question most of the interviews they are asking. Why these two are called universal logic gates? The reason is not any kind of operation it can perform. That is up to Boolean level, basic level, digital logic level. But actual understanding is NAND and NOR are naturally built. AND and OR are not. See here, we have a PMOS logic. This is PMOS logic. This is NMOS logic. Exactly, that is a natural phenomena. So AND operation, OR operation plus negation. What is negation? We have a PMOS logic and we have an NMOS logic. Because the real answer of why NAND and NOR are universal logic gates, the real answer is, after deep understanding of VLSI, what is the correct answer for this question? The answer is, if you connect a PMOS and NMOS in series and the input is commonly connected to an input voltage, it itself gives negation. That is natural phenomena. So in that context, we directly cannot build AND and OR gates. We only built NAND and NOR by nature. Okay. So that is the correct answer for why NAND and NOR logic gates are constructed. Okay. Then see, this is the design process. See, now we are closing. What are the requirements? What are the basics we need to learn from analog side, it is completed. Now coming to digital side, see there are always two parts. One is analog part and always digital part. Okay, now see in digital side how we are constructing them. We have a blocks, implementation technology, design methodologies. These three we are collectively change to get your unified design. Okay, and in Verilog course we first the procedure, first the top to bottom approach is this. This is called the approach to get the actual design. First we have a problem statement. Let's take with an example. Suppose if I want to construct a full adder. So what is our problem statement? An adder which adds 3 inputs and getting 2 outputs, sum and carry. That is our problem statement. It can add 3 single bit numbers. And next we can construct with 3 methodologies. One is gate level, data flow and behavioral level. I am suggesting behavioral level because it is quite easy. Even you don't have gate knowledge or digital knowledge, we can construct with behavioral once you understand the behavior of the adder. What is adder? Adder will do, it takes 3 inputs and 2 outputs. If you know the behavior, you can write the code with the help of if-else construct. That is behavioral model. And then HDL description. That means you can write the code either using Verilog or VHDL. And then hardware implementation. This is out of the bound of this course, but hardware implementation, we have 2 kind of hardwares, FPGAs and ASICs. Okay, so if you have time in your case study, you can implement your design with the help of hardware too. Okay, if time permits, we will go with hardware also. Now, because this course is Verilog, what is the other code we have, other coding style? VHDL. What are the differences between them? We go with it. VHDL and on the other side, Verilog. Both 1981, another one is in 1985. Both are IEEE way of standards are there. And VHDL is particularly good for ASIC. Verilog is industry level language and it is strongly typed. We cannot, even though we missed some kind of syntaxes, it shows the error. But in Verilog, it is like even though we didn't give syntax, some kind of syntax errors, it can auto correct it. Less explicit. That means no need to give clear identification of all. And strong support for package and larger designs, no special extensions. This is general. See, industry is always supporting Verilog well. That's why we have a advanced level system Verilog course is also there. And now, digital basics. What are the important things we need to understand before going to Verilog course? First, you need to understand what is positive number and what is negative number. How they are represented in digital logic. See 12. What is 12? See, any kind of number can be constructed with the help of 8, 4, 2, 1. The given number is 10. Sorry, what is this? 12. What is 12? We just add 8 and 4. 8 plus 4 is 12. Remaining 2, keep 0. That is the way of representing unsigned numbers. That means positive numbers. What is signed? Signed is entirely different. That means, if so for example, if I want to represent -8, what is the way to construct them? We are using 2's complement. 2's complement. Okay, that is we need to understand these basics. For example, if the given number is signed or unsigned, for example, if this is a signed number that is showing here, signed means the MSB is always indicating its negative sign. And next it is 2 square, 0 into 2 power 1, 0 into 2 power 0. So this is -8 and this is +4, 0, 0 and total it is -4. See, 1100 in signed is equivalent to -4. 1100 in unsigned is representing positive number which is 12. Okay, please take care of in which notation they are giving in the exams or when you're listening something, in which form they are actually telling the number is very, very important before writing the codes. And then there are, you know this, decimal, binary, we already, and there is 2 more things which is hexadecimal and octal system. Okay, so these things, most of the students who completed digital logic design have better knowledge with this. So these are the different kind of hexa and octal. You know that octal means 8, so the number of digits are 0 to 7. In hexa, they are 0 to 15, but after 9, we represent them with A, B, C, D, E, F. F means 15. And we have another important thing which is a general representation. What is the difference between ASIC and FPGA? ASIC means it is an application specific integrated circuit. FPGA means field programmable gate array. So ASIC is particularly using for specific applications only. For example, washing machine controller, traffic light controller. It will only do one purpose. It is only doing washing machine related things. Or oven. So inside there is a small microcontroller which is only performing that operations only. But FPGA is not mean that. FPGA we can use for general applications, not application specific. It go with their own kind of designs. Particularly for research oriented things, we are using FPGAs. And this is entire design flow, as this is another important thing to understand what is happening in VLSI. So first we have an idea or problem specification, then we can write the code in behavioral data flow or gate level, because if a design comes to any industry, first they go with behavioral level, they tested it, once it is okay, then they write the code in data flow level, even it is okay, then they go with gate level. Once it is done, then they go with another important model which is not important for our course, that is called switch level. That means transistor level. Okay, that is the basic level of, final level of any design, chip design. Then on one side we have FPGA related verification, on the other side we have back-end design. This is front end, this is back end. What is back end? We are directly manufacturing the actual IC. So what are the things required? First partitioning, floor planning, placement, routing, finally tape out, masking. So this is about design flow. So every time, each step we have verification and feature extraction. Okay, that is completely back end. So that's why in VLSI there are two areas. One is in VLSI there are two areas to settle. One is a front end designer, back end designer. A front end, it is quite easy, but back end it is difficult, because front end supporting digital electronics, back end supports analog part. Okay, thank you.